Welcome, Algebra 2 students, to our second video notes for our second semester. My name is Mrs. Lasner, and I will be going through this outline with you today. Now, don't worry, I'm going to try to keep this one shorter than my note outlines from last semester. And also remember, you are welcome to increase your playback speed when you are watching my videos. Okay, so let's get started. So what are we doing in section 4.2? We are now moving on to multiplying and dividing rational expressions. So you saw this name back in section 4.1, rational expressions, and you may be wondering, what is that? So notice it has the word ratio embedded in there, a rational expression or a rational expression. That word ratio is referring to a fraction. So a rational expression is basically a function that is a fraction, is written as one function divided by another function. I'm just going to call it f of x divided by g of x. Notice that what we have here is a ratio between those two functions, right? A fraction is basically a ratio. Now, one other thing, though, that you need to understand about a rational expression is that it's not a ratio of any two functions, but a ratio specifically of what we call polynomial functions. So it would be f of x divided by g of x, where f of x is a polynomial function. Actually, f of x and g of x, we got to add that in here. F of x and g of x are polynomial functions. And specifically, g of x is not allowed to be 0. So you saw that a little bit in the last video, that if we try to divide a number by 0, the last video it was 2 being divided by 0, that number is undefined. And the closer to 0 that number gets, this value becomes infinitely large. So basically, we look at these expressions, but we exclude any values that would make the function in the denominator equal to 0. So a rational expression is when you have a fraction with two functions where each of those functions are polynomial functions and where the denominator is not 0. Okay, so a really quick review on what a polynomial function is. That I'm not going to give you the formal definition, I'll just show you some examples. But a polynomial function is basically when you have stuff like this, where you have sums and differences, so plus and minus signs, and in between those plus and minus signs are either powers of x, or a product of a number and x, or just a single number, or maybe a single variable. So like x plus 2 could be a polynomial, specifically a binomial because there's two terms, and polynomial just means you could have many terms. So if you have things like that that are being divided by each other, that makes up what we call a rational expression. And so those are the kinds of expressions we're looking at in this video. So the steps for multiplying or dividing, well, first of all, let me say this. We can turn any one of these problems into a multiplication problem. So I'm going to tell you that first. So if your expression is a division problem and not a multiplication problem, then the first thing you would want to do is just turn it into a multiplication problem. So we will multiply by the reciprocal of the second function. So you only do step 1 if the problem starts out as a division problem. If you're dividing, then you basically just turn it into a multiplication problem where you multiply by the reciprocal. Now all the rest of these are what you do when you're multiplying. So what we do first is we begin by factoring. This is why we spent a lot of time talking about factoring in semester 1, because you're going to need to do a lot of it now in semester 2. So we start by factoring all of our numerators and denominators completely, making sure everything is factored fully. We then use those factors to figure out what values of x would make the denominator 0. So we find the zeros of the denominator because we have to restrict those values. So basically we find our restrictions because we have to understand like what values of x this can work for and what values of x it can't. Then what we do is we simplify. And this is important, guys. This is the key. By canceling common factors. factors. Okay, I'm going to stress that in a little bit even more. We do not simplify common terms. We simplify common factors. Now remember, factors implies multiplication. A factor is a number that is being multiplied to something else. Okay, so keep that in mind. That's really important here. So what kind of factors can we cancel? We can cancel binomial factors or monomial factors. Remember, monomial is when you have a polynomial with only one term, and a binomial is when you have a polynomial with two terms. So we can cancel monomial or binomial common factors. Not terms, factors. Okay, so then what we do if we have any leftover factors is we merge any common or any leftover factors by multiplying straight across. Okay, so if we divide, if we are given a division problem, we turn it into a multiplication problem by multiplying by the reciprocal. Now that everything's a multiplication problem, we start by factoring and then using that to find our restrictions. We then cancel our common factors and then we multiply remaining stuff straight across. Factor, restrict, cancel, multiply across. Okay? Now, let me just talk really briefly about what I mean by you can only cancel common factors. So follow me over here for just a moment. So I'm going to show you something here. Let's say I have x plus 5 divided by x minus 2. Now, before you've seen a lesson on simplifying rational expressions or multiplying rational expressions, it might be very tempting for you to say, hey, look, here's a common thing with the numerator and denominator. Oh, look, my x's are the same. I have an x on top and x on the bottom. I'm just going to cancel those out. I'm left with 5 divided by negative 2. This is fantastic. That's just negative 2.5. I'm done. Okay, that is completely and utterly incorrect. Don't ever do that, please. Okay, so that is what you don't do. Okay, so why is that wrong? Like, what's so wrong about it? It looked so right at the time, right? It felt so right, but it was so wrong. Because x is not a factor. Not a factor. Because it is being added to 5. That is changing the nature of x completely, okay? Again, this right here is not a factor. It is not being multiplied to the 2. In fact, the 2 is being subtracted from it, changing it completely. Let me show you what I mean. So let's just say that x was equal to 4. Okay? So let's say x is equal to 4. So then what does this become? This becomes 4 plus 5 over 4 minus 2. Right? Because if x is 4, I'm adding 5 to it. Okay, that's 9. Notice the factors of 9 does not include 4. Right? Factors of 9 are 3 and 3. 4, which was x, is not a factor of x plus 5, okay? 4 is not a factor of 4 plus 5. 4 minus 2 is 2. Once again, the factors of 2 do not include 4, right? 4 is not a factor of 4 minus 2. X is not a factor of x minus 2. And then when I do 9 divided by 2, first of all, it's not negative, and it ain't 2.5, okay? This is 4.5. These two things are not equal. They are not the same. Canceling an x from the top and bottom when it's being added or subtracted to something else is wrong. Don't do it, okay? You can only cancel common factors. Okay, so let me show you what you could do. Okay, what could you do? Well, instead of having x plus 5, let's say it was 5 times x, 5x. Instead of having x minus 2, let's just say it was negative 2 times x. Okay, the fact that these things are connected with multiplication implies that they are factors. 5x has 2 factors, 5 and x. Negative 2x has 2 factors, negative 2 and x. That's when it's okay to say, oh, this is a common factor. It was connected to the 5 with multiplication, not addition. And this x was connected to the negative 2 again with multiplication. So that means that means I can divide them out because it's x divided by x. What is x divided by x? X divided by x is equal to 1. So canceling it out is basically saying, oh, that's going to turn into 1 and that's going to turn into 1. And I'm going to just be left with 5 times 1 over negative 2 times 1, or 5 over negative 2. That would equal negative 2.5. Watch. Now I'm going to plug in again. Let's say x is 4 again. Okay, so what do I have? I have 5 times 4 over negative 2 times 4. Oh, okay, 20. That has a factor of 4, right? Negative 2 times 4 is negative 8. That also has a factor of 4. Okay, I can divide. Well, I could reduce both of those by 4, right, which is what we're doing here. So I can divide both of them by 4, and this would go back to being 5 again. That would go back to being negative 2, and I would have my negative 2.5. This is the same. So when x is being connected to another number with multiplication, or anytime you have things connected by multiplication, and that same factor appears in the denominator and is also being connected by multiplication, then you can cancel them. Because canceling, what that really is just saying, hey, this divided by itself equals 1. That's what we're doing when we are, quote, canceling. We are dividing out to equal 1. In fact, I'm going to add that here. I'm going to say, when you cancel common factors, you really divide those common factors to equal 1. Now, I'm going to probably have to remind you of this over and over and over again, and by golly, that's what I'm going to do, okay? Because if that's what it takes, then that's what I'm going to do. But let's go ahead and start over here with number 1. Okay, first off, when you see something like this, I want you to recognize none of this is factored yet. These are all connected to each other with plus and minus signs. That means they are adding and subtracting, and that means they are not multiplying. So I need to write it as factors to show multiplication. Now these ones here, I can't really do much to factor them. So I can consider each of those a binomial factor. Okay, this is a binomial factor. And I'm going to put it in parentheses to remind myself that these have to stay together. They're connected to each other through addition or subtraction, and they have to stay as one binomial group. So that's why I have them written in parentheses. Okay, now this guy over here, I can factor into 2 binomials by finding 2 numbers that multiply to 6 and add to 5. Multiply to 6 and add to 5, I'm thinking 2 and 3. So I can write this as x plus 2 and the other one as x plus 3. So this turns into that. The x squared minus 9 I can also factor into 2 binomials because it is a difference of squares. You may remember from Unit 1 where it's x plus 3 and x minus 3. Or you can say, what would multiply to negative 9 and add to 0, right? Because the middle term is missing. Well, that would be a 3 and a negative 3. So that's why there is no middle term. I need one positive 3 and one negative 3. Okay, so what do I have right now? I have x minus 3 times x plus 2 times x plus 3 over x plus 2 times, right, because I'm connecting these fractions through multiplication. So basically everything on the top is multiplying together and everything on the bottom is multiplying together. That also means that anything on the top can divide with anything on the bottom if it's a common factor, because these are all being connected through multiplication. And I notice that there is a common factor of x minus 3 on the top and bottom, so those divide to equal 1. There's a common factor of x plus 2 on the top and bottom, so those divide to equal 1. There is another common factor of x plus 3 on the top and bottom, so in this particular example, literally everything canceled out, and I'm left with 1 over 1, which is 1. Wait a minute, I realize I forgot something in example 1. It mentions that we need to find the zeros of the denominator, and I accidentally left that part out in example 1, so let's figure that out right now. The zeros of the denominator would be anything that makes x plus 2 0, or x plus 3 0, or x minus 3 0, because those are the 3 factors in my denominator. Here's x plus 2 and then x plus 3, x minus 3. So basically I'm not allowed to let any of those factors end up being 0. So this one would be 0 if x were negative 2. This one would be 0 if x were negative 3. And this one would be 0 if x were positive 3. So my restrictions for number 1 is x cannot equal negative 2, negative 3, or 3. So in other words, these factors can all divide and cancel from each other to equal 1 as long as x is none of these 3 values. Because if x is one of these 3 values, I would end up dividing by 0, which is not allowed in division, basically. So I can't let x equal any of these 3 numbers. So for all other x's, then this problem will multiply together or divide together to equal 1. Okay, so now we can move on to number 2. So again, number 2 is a multiplication problem, and I need to start by factoring. Notice in the denominator, the 2 and the x are being connected to each other through multiplication. So this denominator is already factored. It's a factor of 2 times a factor of x. It's the things that have like plus and minus signs that we need to look at and factor. Those are the things that are not currently factored. So looking at this first numerator, it looks like all I need to do for that is take out a GCF. There's a common factor of 2 between 4 and 2, and then a common factor of x between x and x squared. So I can take out a 2x, and I would be left with 2 minus x. Then for that denominator, this would be a little bit longer of a factoring process because my a value is not 1. So I would have to multiply 2 to negative 15. I'll give you negative 30. And then find 2 numbers that multiply to negative 30 and add to 2. So I could try 15 and negative 2, but that would add to 13, so that won't work. I could try 10 and negative 3, but that would add to 7. I could try 6 and negative 5, but that would add to 1. So actually I'm thinking this denominator part is not going to factor. So then it's basically already as factored as it's going to get. So you could think of it as a trinomial factor. So I'll just have to keep all of those pieces together because I'm not able to factor it at least into rational number factors. Okay. But the numerator of the second fraction I can factor because I can find 2 numbers that multiply to 3, right? Multiply to c because a is 1. And add to negative 4, it would be negative 1 and negative 3. If I make both of them negative, they'll multiply to positive 3. And then when I add them up, they'll add to negative 4. So I have x minus 1 and x minus 3. And then that's being divided by 2 times x. I'm going to put that multiplication there just to emphasize the fact that they are factors. So it looks like I can't really cancel any of my binomial factors, but I can cancel the 2 and the x from this denominator. And the rest of it I just multiply straight across, back together with each other. Oh wait, I did it again. I have to find the zeros of the denominator. Or the restrictions, I guess you could say. So I know from this denominator over here, right, x is a factor, so I can't let that be 0. So one restriction is that x can't be 0. Now for this one here, it looks like I'm going to have to find those zeros using the quadratic formula because it didn't factor nicely. So I'm going to have to find those zeros using the quadratic formula. So I plugged in 2 for B, another 2 for A, and then negative 15 for C. So in here I get 4, and then this subtraction turns into addition. So 4 plus 8 times 15 gives me 124 inside my radical, all over 4. And then of course I can simplify my square root a little bit. So I can take out a 2, since that's the square root of 4. So I have negative 2 plus or minus 2 square root of 31 all over 4. And then since I have a common factor of 2 in my numerator, I can factor that out, pull that out from the numerator, leaving me with a negative 1 from here, and then a plus or minus 1 times the square root of 31 from here. This is all being divided by 4. Now see, since this 2 is being connected to the rest of the numerator with multiplication, that makes it a factor, so I can reduce it with the 4. So it looks like my other restrictions, the other values that x cannot be, would be the solutions to this equation here, which are negative 1 plus or minus the square root of 31 all over 2. So x cannot be those numbers either. So as long as x is any other values besides these 3, then I can cancel these out here and multiply the rest of it straight across to give me my final answer of, and you don't have to FOIL these, you can just leave them factored. So it would be 2 minus x times x minus 1 times x minus 3 in the numerator. And then all of that is being divided by this quadratic, divided by 2x squared plus 2x minus 15. So then moving into example 3, maybe what you would notice here is that the problem I have now is a division problem. I'm taking this first fraction and dividing it by the second fraction. So according to our steps, if we're confronted with division, we basically turn it into a multiplication by the reciprocal problem. So this currently is division, but I'm going to change it into, so the first fraction stays the same, 2x plus 6 over x squared plus x minus 2 times, so I'm changing this into multiplication by the reciprocal, because that's what it means to divide by something. It means you're multiplying by the reciprocal. So then the old denominator, x squared plus 3x plus 2, goes in the numerator, and the old numerator, x plus 3, goes in the denominator. And I'm going to put parentheses around it because we need to understand that this is a full factor. It cannot be factored into smaller parts. Now let's go through the rest of these things to factor them. So over here, the 2x plus 6, I notice I can take a 2 out between the 2 and 6. So I'm going to do that. So this becomes 2 quantity x plus 3. In my numerator, I just need to find two numbers that multiply to negative 2 and add to 1. So for this one, it would be positive 2 and negative 1, because if I multiply them, I get negative 2, and then if I add them, I get 1. So I'm going to factor it into those two factors, x plus 2 and x minus 1. So this first fraction is finished. Then for the second numerator, I have x squared plus 3x plus 2. So I need to find two numbers that multiply to positive 2 and then add to 3. So now I'm thinking it would be positive 2 and positive 1, because if you multiply two positives, you get a positive, and then if I add 2 and 1, I get 3. So those factors would be x plus 2 and x plus 1, and all of that's being divided by x plus 3. So everything now is factored, everything is being multiplied to other things. Nothing is being connected through addition or subtraction anymore. So I can begin to cancel things. So I am going to cancel the factors of x plus 3 with x plus 3. So they divide together to equal 1. I can also cancel the x plus 2 in the numerator with the x plus 2 in the denominator. Those cancel to equal 1. Now you might be wondering about the x minus 1 and the x plus 1. Those are not the same factor. Yes, they both have x and x. Yes, they both have 1 and 1. But the act of adding versus subtracting makes these numbers different. So remember earlier when we were kind of using like x equals 4 as a sample? If I had 4 plus 1, that would equal 5, right? No common factors of 4. If I do 4 minus 1, I get 3. So 5 and 3 have no common factors with each other because the act of adding 1 changed the nature of x to something completely different than when I subtract 1 from x. So those factors are not the same and therefore cannot be canceled. So my final answer would be to just multiply these remaining factors together straight across. So it would be 2 times x plus 1 in the numerator, all divided by x minus 1 in the denominator, and that's my final answer. Of course, there are restrictions on this one, and also when we're looking at restrictions, we have to look at all denominators ever. So I'm going to kind of highlight all denominators ever. So remember the x squared plus 3x plus 2, which ended up in the numerator, but it used to be in the denominator, so its factors, x plus 2, x plus 1, I cannot let either of those be 0 because they were at one time in the denominator. Meanwhile, I have these other denominators, right? X squared plus x minus 2, that factored into x plus 2, x minus 1. And then when I flipped this fraction over, the x plus 3 that was on top ended up being in the denominator. So basically, anything that would make any of those highlighted factors 0, I can't let x equal that thing. I cannot let x equal negative 3 from the x plus 3. I cannot let x equal negative 2 or negative 1 from the x plus 2 and the x plus 1, which was the same here, and I cannot let x equal 1 from that factor. So it's kind of like I just took any factor that was ever in the denominator at any time, whether it was in the beginning problem or the end of the problem. I think that covers all of them. This one, this one, this one. This is the same in that one. If any of them are 0, that's a restriction. So this one here, I can't let x be negative 3. This one here, I can't let x be negative 2. I can't let x be negative 1, and I can't let x be 1. So those are my restrictions. So why don't you guys try number 4? Try simplifying it to see what the final expression would be. Okay, so hopefully the first thing you did was turn the division into multiplication and then multiply by the reciprocal of the second fraction. So the x cubed plus x squared should end up in the denominator, and then this x should end up in the numerator. Then hopefully you recognize that the numerator was a sum of cubes and factored it using our SOAP formula, or sum of cubes factoring formula. Then in the denominator, all I could really do was factor an x squared as a GCF out of x cubed plus x squared. So that was right here. Then the x in the numerator of the second fraction canceled with one of the x's in the denominator of the second fraction, leaving behind one x left right here. The x plus 1 in the denominator never canceled, so it was still there in our answer. Then we had a factor of x plus 3 in the numerator when we factored using sum of cubes formula. That canceled with the x plus 3 in the denominator, but left behind this part. The x squared minus 3x plus 9 was in the numerator. So this here is our final answer. Now, I wonder if you could also tell me what are the restrictions for this problem. Okay, so the restrictions for this problem should be 0, negative 3, and negative 1. Why is it those? It's because you have to look at any denominator that was ever in the problem at any time from beginning to end. In the beginning, I had x plus 3 and x in the denominator. So that means x cannot be 0, and neither can x plus 3. But then when I flipped that second fraction over, x cubed plus x squared ended up in the denominator, which has the factors x squared and x plus 1. Well, x squared not equaling 0 is pretty much the same thing as x not equaling 0, so those kind of go together. But then there was this addition of x plus 1 is not allowed to equal 0. So if I solve all these for x, then I get, okay, x can't be negative 3, and x can't be negative 1, and right here it says already x can't be 0. And if x can't be 0, then that would automatically include x squared not being allowed to equal 0. So these are our 3 restrictions for number 4. Now number 5 probably looks really strange because it's like a fractions inside of a fraction. But this division symbol, or this fraction bar right here, the one in the middle, the one separating the two fractions, is just another division symbol. So this is basically a division problem written as a fraction, right? Every fraction is a division problem. So what we want to do is start by rewriting it. Maybe it would help for the first time, rewrite it as a division problem. with a division symbol versus a fraction. And then recognize, okay, I just need to flip that second fraction or that bottom fraction over and change it from there into a multiplication problem. So we're going to multiply by the reciprocal of the second fraction. Now for factoring, it looks like some of these are already kind of factored, right? The ones that don't have any plus or minus signs. And then the only two that do have minus signs, looks like the only thing I can factor would be GCFs. I can take a 2 out of this first one. I can take a 5 out of the second one. And then I'm left with 2 times the quantity 3 minus x. And then maybe I'll write x cubed out as x times x times x. So you can kind of see it's basically 3 identical factors of x. And then in the numerator, I'll write it as x times y because it's one factor of x and then 2 identical factors of y. And then in the denominator, I can take out a 5 and I'm left with x minus 3. So I recognize right away that one of the common factors I have is x with x. So there's no more x's left in the numerator, but there are still 2 left in the denominator. And there were no other factors of y, so those are basically going to stay in the numerator. And then I notice an x minus 3 and a 3 minus x. So what I want to tell you guys about this type of factor is that they are not quite the same. They are almost the same. But what I'm going to have to do to be able to cancel them out, to be able to make them the same, is I am going to have to factor out a -1 from 3 minus x. Because x minus 3 and 3 minus x, the only thing that makes them different is an extra factor of -1. So I think I'm going to take this part right here, the 2 times 3 minus x, and I'm going to factor out a -1 from the 3 minus x. So maybe I'll keep the 2 on the outside for a minute, and I'll take a -1 divided out from both 3 and -x. So when you divide a -1, or when you divide 3 by -1, it turns the 3 into -3. When you divide -x by -1, it turns it into +x. Because remember, factoring a number out is the same thing as dividing it out from the 2 terms inside the parentheses. So now I have basically a -2 in front, right? The 2 that was already there times the -1 that I factored out times -3 plus x. So essentially, all that happens when you factor out a -1 is you just change the sign of each term inside the parentheses. So why is that what I needed to do here? Is because that's all that was different between 3 minus x and x minus 3, was the signs of the terms. Here 3 is positive, here 3 is negative. On this one, here x is negative, but here x is positive. So if I factor a negative out of this top one, it changes the signs, and now I have, okay, a positive x and a -3. And since these are basically just being added, I can reorder them and write it this way, positive x plus -3, or x minus 3. So changing the signs of the terms inside the parentheses basically changes the order of the subtraction. The 3 minus x reversed order and became x minus 3 when I took out the -1. Okay, so now what do I have in the numerator? Now I have a -2, so this is -2 times x minus 3 all over, well, now I have x squared, right? I had x cubed, now it's x squared, times, I have my y times y, so times y squared over 5 times x minus 3. And now that I've taken out that -1 and recognized that this really contains a factor of x minus 3, that's a common factor that I can now divide out to equal 1 or cancel out. And so the remaining factors in my numerator would be -2 times y squared. So I did have a negative, I'm going to have a negative left over in my answer that was not there earlier, right? So to switch the order of subtraction, it did introduce a negative to my problem. There's a remaining negative there, but it did allow me to cancel those factors out. And then in the denominator, I have x squared times 5. So that is my answer to this division problem, right? I do need to list the restrictions. So remember, when you are finding restrictions for these types of problems, you need to look at all denominators ever. So I have my x cubed was a denominator from this first fraction. my xy squared was originally the denominator of my second fraction. It did end up in the numerator, but it was a denominator at one point. And then the 5x minus 15 became a denominator when I flipped that second fraction. So my denominators were x cubed, xy squared, and 5x minus 15. So if I set those factors equal to 0, here basically x cubed, I can't let that equal 0, so that basically means I can't let x equal 0, right? Because if I were to solve it by taking a cube root, I just get the cube root of 0, which is still 0. Or you can think of it as x times x times x, right? X cubed is x times x times x. So basically it's just 3 times saying, okay, x cannot be 0 3 different times. So basically x can't be 0. So that already takes care of this x from that other denominator. We also have y squared can't be 0, right? So what does that imply? That implies y times y cannot be 0. What does that imply? That implies that y can't be 0. Then the 5x minus 15, if you remember when we factored that, it was right here, was 5 times x minus 3. So I have these factors of 5, but 5 already can't be 0, right? That's not something we need to worry about. 5 is not 0. But then there's x minus 3. I can't let that be 0. So that means I cannot let x be 3. So my restrictions for number 5 are basically x cannot be 0 3 times, y cannot be 0 twice, and x cannot be 3. Now, last but not least, in example 6, we are finding the area. So what we're going to have to do is multiply base times height, because the area of a rectangle would be the base times the height. So it looks like this rational expression is my base. This rational expression is my height. So if I want to find the area of this rectangle, given that base and height, I basically need to multiply these rational expressions together. But we've learned some tricks of the trade today for multiplying rational expressions. So why don't you guys go ahead and try this one? Go ahead and get the simplified answer first, and then we'll look for restrictions. Okay, so to multiply these expressions together, of course, we'd have to find the factors of each numerator and denominator, because they were all separated by additions and subtractions, and we wanted to change it to have everything separated by multiplication. When we do that, we notice quite a few common factors. We had a v plus 6 in common. That could cancel, and we had 8s in common, that could cancel, and v plus 3s in common, that could cancel. Our leftover factor in the numerator was v minus 7, and we had 2 leftover factors in the denominator of 8 times v, and that was our remaining expression. This represents the area of that rectangle. Now, why don't you go ahead and also find the restrictions for this one? Okay, so to find our restrictions, we zero in on our denominators, and we recognize that we don't want those denominators to be 0. So we have to factor them, or we already factored them, and we look at each of the factors, we set each of the factors equal to 0, and then figure out what value of v, in this case, would make them 0. Well, our first factor was 8, but 8 is never going to be 0, so that's done. We don't need to worry about that one. We only worry about the variable factors, right? Those are the things that could end up equaling different values at different times, and so we watch out more for those. So there was a factor of v. We cannot let that be 0. There was a factor of v plus 3. We cannot let that be 0. And there was a factor of v plus 6. So v can't be 0, and then from this one it can't be negative 3, and then from that one it can't be negative 6. And that concludes our video notes on section 4.2, and I will see you guys in class.